For today's lesson, we're going to talk about counting techniques, and these are your permutations and combinations. I'm going to refer to putting objects in boxes or people into boxes. This is not standard procedure, but it can help you understand the counting that is taking place. The reason I do this is to avoid, the reason we do this type of counting is to avoid having to count each individual outcome when there could be a considerably large number of outcomes. So, multiplication rule for counting. The fixed price dinner at Mabenka restaurant provides the following choices. You get either a soup or salad, you get one of 4 entrees, you get ice cream or cheesecake, and how many different meals can be ordered, or different combinations of these meals. Since we're making a meal with one item from each category, we need 3 boxes, and rather than list out all possible meals, we can do this rather quickly. So I'm going to show you what it would entail if you were not doing the box method. So you'd write out soup, you'd write out each of the entrees, you'd write out each of the desserts in each section, because once you get your entree, you get one of the desserts, and then over here is each meal choice or decision that you've made. There are 8 of them. Now notice this is only for soup. There is still one for salad. It would be too big to put salad on this slide, so I decided to cut it off. So there are 8 here, so that means there's another 8 for salad where soup is replaced with salad, and so there are 16 total. What this means for you though is if we go to our box method. So I said in the original slide that we need 3 boxes. Then what that means is we're going to draw our 3 boxes. Okay, and this makes one meal. And so you had 2 choices for soup or salad, so that's 2. You had 4 choices for your entree, which is 4, and then you had 2 choices for dessert. So if you multiply these all together, you get 8 times 2, which is 16, and you can get that rather quickly. This also works if you're doing things like choosing an outfit where you have a certain number of pairs of pants and shirts and socks or something, or shoes. And so you can do this method using, you can also use this counting method on that as well. If we keep going, then if tasks consist of a sequence of choices in which there are P selections for the first task, choice, Q selections for the second, R selections for the third, and so on, then making a task, then the task of making these selections can be done P times Q times R times ... however many choices you have, different ways. That's what the multiplication we just did was. An example with repetition. So we've got the International Airport or Air Transportation Association assigns 3-letter codes to represent locations. For example, the code for Fort Lauderdale is FLL. How many different airport codes are possible? Okay, so first things first. Obviously, L can be used multiple times, and any letter can be used multiple times for that reason. And since there are 3-letter choices, then what's going to happen is we have 3 letters we're going to put into each code. And since we're only able to use letters, there are 26 letters in the alphabet. So the first one you can have 26. The second one you can have 26, and the third one you can have, that's a 3, 26. And so if we multiply that together, that's 26 to the third, which I don't know that off the top of my head, so let me calculate real quick. 26 times 26 times 26 is 17,576 ways, or different combinations. There are 1,700 or 1,576 different airport abbreviations that they could use technically. Okay, so, and that includes ZZZ, which I don't know what you'd call ZZZ, but maybe the sleep airport or something. So, I hope that makes sense. Obviously, it would be a different problem if there was no repetition, so let's look at one without repetition. So we have 3 members from a 14-member committee are to be randomly selected to serve as chair, vice chair, and secretary. The first person is selected selected is the chair, the second person is the vice chair, and the third person is the secretary. How many different committees are possible with 14 people? So let's go back. We've got a 3-person committee. We've got, oops, that's the eraser still. President, VP, secretary. And if we're going to do this, then there were 14 people to choose for president. Maybe all of them want president. Then once that person's chosen, there are now 13 left to choose, and then there are now 12 left to choose. So if we multiply that together, we have 2,184 ways to choose a committee of 14 people from 14 people of 3 important positions. Okay, so that's taken care of. Factorials, we're going to talk about this first before we talk about permutations and combinations. Those were both examples of those things, sort of. We have factorials. If n is greater than or equal to 0 is an integer, then n factorial is defined as follows. N factorial is equal to n times n minus 1 times ... times 3 times 2 times 1. So all you're doing is multiplying every consecutive number down until 1. And then also one thing to note is by definition 0 factorial is 1 and 1 factorial is also 1. So there's 2 things that are the same. And let's give you some examples of this. If we're looking at factorials, I could say 5 factorial, which is equal to 5 times 4 times 3 times 2 times 1. We multiply all this together. This is 26, and that's 120. Okay, and then if you wanted 6 factorial, well, that's 6 times 5 times 4 times 3 times 2 times 1. And so you'd get, this is 720. Now, one thing to note, you can write 7 factorial as 7 times 6 factorial. And we know what 6 factorial is. We know this is 720. So we would just have to do 720 times 7, which I don't remember what that is off the top of my head. 7 times 720 is 5040. And it is very important that you be able to break this down in these ways because factorials will have division in them, and it's easier to divide 6 factorial by 6 factorial than it is to have to write it out every time and cancel each individual thing. So like I'm saying, if you have 6 times 5, 3 times 2 times 1, rather than have this, then you just go through and cancel each individual one. I mean, you can technically do this, but it's a lot easier to have 6 factorial and then 7 factorial, and then just write this as 6 factorial, 7 times 6 factorial, and then cancel that, because that would leave you with 1 over 7. Okay, that's a lot quicker. Oops. So, sorry, I'm looking at my YouTube comments and I'm getting spam bots that are posting dating sites or something like that. Next one, you have just been hired as a book representative for Pearson Education. On your first day, you must travel to 7 schools to introduce yourself. How many different routes are possible? So let's go back. We're going to do this again. I'm just going to clear this. So we've got to go to 7 schools. Okay. And if we've got to go to 7 places, well, and how many different routes they're asking? Well, depending on where you start, you're going to have a different route. So there are 7 choices for the first one. Then the next school you go to is 6, 5, 4, 3, 2, 1. So this is really just 7 factorial, which is equal to 5040 ways. And therefore, that is the number of ways you can go to different schools. So let's go back. Now let's talk about permutations. The number of permutations of n distinct objects taken r at a time. The number of arrangements of r objects chosen from n objects in which the n objects are distinct. Repetition of objects is not allowed, and order is important is given by the formula npr is equal to n factorial n minus r factorial. Permutations order matters, so this is an example like where you're going to different schools like we just did, or you're making different routes, because if you start one place, then the next place you go to, the order you do it in matters. Permutation position may help you remember this, and that position of the objects matters. So, example problem. You have just been hired as a book rep. So this is the same one we just talked about. Ask yourself, does order matter? In this case, if I go to school A before school B, I have taken a different route than if I go from B to A. So yes, order matters. And if you're going to use permutations on the calculator, you're going to push, I'll go through this with you real quick. Sorry. Since I have access to a computer, what we can do, let me find my calculator real quick. Okay. Okay, so you push second. Actually, no, you push math. Just push math. You don't have to push second. Go to probability. NPR. N is the number of objects you can choose from, 7. And then, oops, sorry. So if you do that, make that mistake, you can just push second and enter, and it'll bring back what you had. 7, choose 7. And you can see that there are 540 ways. If we only had to go to 3 schools, then it would be 7, choose 3, which would significantly lower your choices, I believe. So if I do that again, let's pretend we only had to go to 3 of the 7 schools, not all of them. 210 ways, and so on and so forth. Let's go back to the PowerPoint. This obviously shows that this was right before the shutdown from the schools last semester, but obviously you decide if it matters. You go to math, probability, and then NPR, and then you can take that. And so examples of permutations, I wanted you guys to do that on your own. Obviously, you've just seen me do 7, choose 3, so you can hopefully do that on your own. Practice that. Let's look at another one. In many ways, how many ways can horses in a 10 horse race finish first, second, and third? First of all, does order matter? And obviously it does, because if I bet on one horse being in first place, one horse being on second, and one horse being on third, if they come in any different order than that one that I have chosen, I probably am not going to win my bet, unless it's some kind of bet where you only choose in the top 3. So order does matter. There's 10 horses, so let's think about this with the whiteboard real quick. So remember, we're choosing first place, second place, and third place. And there are 10 horses, so 10 horses can technically come in first, 9 can come in second, and 8 can come in third. What does this look like in terms of a permutation? Well, this is 10p3, which means it's 10 factorial over, it's 10 minus 3 factorial. Okay, so this is 10 factorial over 7 factorial, which is 10 times 9 times 8 times 7 factorial over 7 factorial. Cancel, cancel. Well, look at that. 10 times 9 times 8, that's exactly what I got with the boxes earlier. Maybe the boxes are easier for you to understand. Maybe the formula is easier. Either way, it's fine. And this is 720 ways for the 10 horses to come in first, second, and third. Okay. Let's check. Are we getting into combinations? Yeah, we're going to get into combinations next. So I'm going to go ahead and stop this video here. I hope you guys are practicing. Make sure you're doing this. Thank you, guys.